In the previous episode, we talked about the ideal idea that averaging multiple gyroscopes can reduce gyro reading noise. But reality is much harsher, especially when dealing with analog circuits, which are far more complex than digital ones. So when we look at a real flag controller with two gyroscopes on it, in theory, it should reduce noise according to variance and standard deviation. However, this is based on the assumption that the two gyro readings are independent and identically distributed. In reality, there are many reasons why the gyros are no longer independent. For example, both gyros may be powered by the same LDO. Any noise generated in that power supply will affect both gyros at the same time, effectively coupling and amplifying the noise between the two sensors. At this point, we can no longer simply apply the square root rule to estimate noise reduction. We must introduce covariance, the correlation between the readings of the two gyros. If the two gyros are placed far apart, are truly independent, and powered separately by ABEC, then we can assume the covariance between them is zero. This brings us back to the ideal formula we discussed earlier. As the number of gyros increases, the white noise theoretically decreases by a factor of 1 over the square root of n. But in the real world, some dual gyro flag controllers are designed very differently. The two gyros are placed extremely close together and even oriented in the same direction. On top of that, they are powered by the same LDO. Under these conditions, the correlation between the gyro readings becomes very high. In extreme cases, the covariance can become so large that the system effectively degenerates to the variance and standard deviation of a single gyro. In other words, under these conditions, two gyros offer no noise advantage over one. That's why more forward-thinking manufacturers take hardware design seriously. They may place the two gyros orthogonally and power them using separate LDOs. This minimizes the correlation between the two gyros as much as possible. This allows the statistical noise reduction we discussed in part 1 to actually work in practice, and finally reach the ideal result, reducing noise to about 0.707 times the original level. That's our analysis of dual gyroscopes, both in theory and in real-world hardware.